Good morning, ladies and gentlemen. This slide is a bit of review, linear motion, circular motion, and angular motion, and I want to talk about each of these. So linear motion is what we've been working on, well, not been, but in the past. Velocity, the displacement, time, well, time's for all of them, and acceleration.
It's like number lines.
Yeah.
X and Y axis.
All our kinematic stuff. Then we moved on to circular motion.
Yep.
And we have a radius and we have a velocity that is tangential to the circle, our path. And then our centripetal force is in the same direction as our centripetal acceleration.
Yep, toward the center. That's what centripetal means.
And then what we're talking, our new topic is angular motion. And what we have here is we have an angle that covers a certain amount of distance through that arc length.
Yep.
Oh, and it's represented by this equation right here. And we saw this yesterday.
Yep.
And what I really want to point out to you guys is these two are living in parallel universes.
Just like on the next slide.
Yeah. Emphasis, linear and angular motion are parallel universes, kind of like how Marvel has the different parallel universes of all their comic stuff going on. Things are similar and they act the same but in their own universe.
Yep.
Angles can be measured in degrees or radians, and so you guys are familiar with this conversion.
Yeah, we did that mess yesterday. You can make two fractions out of that.
Just a little bit of review. The arc length, S, traced by a point depends on the radius, R, and the angle, angle is in radians. And that's represented by this equation right here. The S equals the R times the theta.
The S is like the stripe on the ground that the wheel leaves.
The stripe on the ground that the wheel leaves, yes.
Remember this saying? You got the, here, I'll let you do this.
Okay, so we started off, where's the blue? Can you see the blue? Okay, right here. And when we said go, it'll leave the stripe on the ground, boop, that's one revolution.
Yep.
Right there.
If we had a bigger wheel, it would go farther in one revolution.
We'll put that right there. We'll come back to that. Okay. Linear displacement is the change of positions. We know this, right? Final minus initial gets me the change in the displacement.
You go from that place to this place, that's a displacement.
Yeah. Now, in angular displacement, we're looking at the angle. And these two things are similar. They're parallel, right? They act the same in their universe. So instead of displacement, we're talking about the angular displacement.
So instead of the change of position on the number line, we're thinking about change of angle.
Yeah. So from here to there,
Good.
right?
Yep.
And these are they're the same thing. Not same, but similar.
Yeah.
Okay? They act the same.
Yeah.
Angular displacement is a vector quantity, like the unit circle. Counterclockwise is positive, and the other way is negative.
Yeah.
We already saw this slide, but this time you've got the one revolution in there.
Yeah.
So there's a relationship between these things, and you can convert from one to the other.
As it goes around once, one revolution, it covers 360 degrees, which in a different language is 2 pi radians.
2 pi radians, okay. A bicycle with 0.34 meters radius wheels moves forward 10 meters. What is the angular displacement of the wheels?
How many radians is subtended by such motion?
Ooh, subtended, that word. Let me get rid of that. Okay, so I'm gonna put this over here. Okay, so a bicycle with a radius of 0.34 meters moves forward with 10 meters. That's probably gonna be my S.
Well, that's the stripe it leaves on the
The
ground.
stripe on the ground, absolutely. And then what is the angular displacement of the wheels?
Yeah.
Okay. And we know that S equals R angular displacement, and we can just divide by the R to get that by itself. My S is 10 meters, stripe on the ground, My R is 0.34 meters. Thank you, sir. Okay, so 10 divided by 0.34, and I get 29.4.
So 29.4, and what are the units going to be? I noticed the meters cancel,
We don't have any units for
but
radians.
the units of angular measure is radians, so that should
Oh,
be
sorry, radians. That's right. They cancel out completely, but they create radians.
simple, no?
Yes, it's easy. Okay. Moving on. How many revolutions is that?
We need to make a conversion. Let's see. 1 revolution is how many radians?
I'm gonna do some blue. 1 revolution is equal to 360 degrees, or 2 pi radians.
Yeah.
So I'm just gonna go ahead and take this 29.4 radians and make my little chart. I'm gonna put 2 pi radians on the bottom, 1 revolution on top. My radians cancel, and I'm just gonna do 29.4 divided by 2 pi. 29.4 divided by parentheses 2 pi, and I get 4.7.
So it goes around 4.7 times. Good morning. So as it rolls, it goes around.
It goes around. Wait. Goes around. 1, 2, 3. Ow. 4,
0.7.
6.
4.7.
So as you can imagine, 10 meters is a long ways to go. So
That's
it's going
right.
to go around a couple times.
Yeah.
Okay. Linear velocity is the rate of change of position. This is review.
Y'all know that. You're comfortable with
Velocity
that.
equals distance over time, meters per second. Okay. No. Angular velocity
Which is symbolized by the Greek letter omega. Looks like a W.
is the rate of change of angle around a fixed axis.
That equation has different symbols.
Okay, it's got this omega for angular velocity. Now check over here. We're just talking about velocity here, linear velocity,
Notice how they're the same.
angular velocity. Not much has changed, just the letter, symbol we're using. Now we said this was angular displacement, right?
Yep.
Over here,
It
linear
says
displacement.
Linear displacement. You got meters per second for linear, radians per second for angular.
Time is the same. So yeah, I mean it's the same concept, right?
Yep.
Okay. Let's watch this video. This more is ready. I'm gonna make sure my volume's good though.
Make it big, make it big.
Oh yeah. So here we go.
That's Plato.
In ancient times, the Greek philosopher Plato declared the circle ideal and asserted that all other forms were imperfect, inferior representations. He decided circular motion describes the heavens,
His eyes are
not
weird.
merely circular motion, uniform circular motion. Each heavenly body was to be a point moving on a circle at a constant rate. Viewed another way, the vector is at an angle that grows at a constant rate. That rate, omega, is known as the angular speed of the object. So at any time t, the angle theta equals omega t. In 1 revolution, the object moves through 2 pi radians in time capital T. Therefore, the angular speed is 2 pi over capital T.
Okay, let's watch that again. Oh, we good?
Yeah. Well, I was going to say the key here is the time to go around once. That's the period. But go ahead, let's watch it again.
Let's watch it again, and this time I'm gonna pause it a few times
I like that.
to kind of go over some stuff.
We need to go by.
The Greek philosopher Plato declared the circle ideal and asserted that all other forms were imperfect, inferior representations.
He's got terrible
He
complexion.
decided circular motion describes the heavens, not merely circular motion, uniform circular motion.
I love this.
That's
music.
because of perfection. How fast is that
Each
going
heavenly
around?
body was to be a point moving on a circle at a constant rate. Viewed another way, the vector is at an angle that grows at a constant rate.
Okay, pause here for a second.
Yeah.
So think about our velocity versus time graph, right? It shows
Yeah.
our velocity versus time is distance and time, right?
Yeah.
And so the only difference here is that we have our angular displacement instead of linear displacement.
So and that slope tells you, if it was a shallower slope, that would mean it's going slower, and a steeper slope would mean it's going faster, right?
Yeah, and the slope is just telling us, well, in linear velocity, d over t is in regular linear motion, d over t is velocity. In angular, our angular displacement over time is still velocity, but we just call it angular velocity.
It's how fast it's going around.
Yeah.
It's exactly the same thing. It just looked like it's Chinese.
That rate, omega, is known as the angular speed of the object.
Yep.
So at any time t, the angle theta equals omega t.
Okay, what did they just do? So they basically just multiplied by t on both sides. They just spit out, they just did this for us, what they say, equals, they put like this. Okay, they just multiplied on both sides and canceled stuff out here.
Okay, now, yeah, go ahead. No, go ahead.
So,
Let's,
anything to add there? Speed?
no, we'll get to the stripe here in a minute.
Do you want, well, let me just add one other thing up here. This is just like saying v equals d over t, right?
Yeah.
And then we just flip some things around here. If you were gonna try to get this by itself, right, it'd be just
Multiply
like
both
this.
sides times t.
And that's all we're doing here.
Yeah.
That's what I was trying to remember.
If you drive 60 miles an hour for 1 hour, you go 60 miles. That's all that is.
In one revolution, the object moves through 2 pi radians in time capital T. Therefore, the angular speed is 2 pi over capital T.
You stop it right there. Yeah, so that
They said you move through 1 revolution and 2 pi, right?
2 pi radians, and the time for one revolution is called a period, which is symbolized by capital T. See the little t and the capital T?
So what they did here was I'm gonna actually erase this part up here. You know, how'd they get that equation? Okay, I'll pretend like I didn't do this. Okay, divided by t. Was they said, well, so 1 revolution, that's gonna be one whole angular displacement,
Yeah.
right? So basically 1 revolution, 2 pi, they put that up there, divided by t. Instead of time, it's the period.
It's the time for go around once.
Yeah.
It's a simple thing.
So that's all there is to it. That's what the video is talking about. I think we're done here, yes?
Yes, we are done with this.
I'm going to exit out of this beautiful thing and move right along. Okay, so the bicycle.
What bicycle?
This bicycle right here.
Oh, that we've already done.
Actually, no, this bicycle, sorry. The bicycle, which has a radius of 0.34 meters, and we said that its angular displacement was 29.4 radians. That bicycle.
As it goes 10 meters down the street, leaves a stripe 10 meters long.
Okay, and up here it says the bicycle is moving at 3.6 meters per second. Okay, so the velocity here is 3.6 meters per second.
So we just use that equation up there, distance over time, and we want to solve for time.
Wait, was this the one that we wanted to
Yeah,
keep
yeah,
it
no,
just
no,
like
no,
this,
no,
right?
no, no.
Yeah, okay. Okay, so let's go ahead and solve for time. So this is just linear, right?
Yes, it is.
So v equals d over t. If I want to solve for time, I just can flip these bad boys. So time is my distance, which is how far? 10 meters? Yeah, 10 meters. Sorry, it's in the question right there. Distance equals 10 meters. Right there, number 1. 10 meters divided by my velocity, which is 3.6 meters per second. So if it's going 3.6 meters per second and it goes 10 meters, how much time did it take to do that? 10 divided by 3.6, and I get 2.77. I'll call it 2.8.
2.8 seconds. So it goes 10 meters in 2.8 seconds because it's going 3.6 meters per second. But during that time, while it's going 3.6 meters, the wheel turns through 29.4 radians.
And what does that mean? Well, don't forget, a radian is just the same thing as it's the same thing as a 2 pi radian. It's the same thing as revolution, or it's 36 degrees. So 29.4 radians. It's
Yeah.
spinning, right? It's moving around in a circle, angular, okay, around that axis. So now it says, what is the the angular velocity of the wheels, well, let's go back to our equation. We had the change delta over this, right? Like this is my equation, right?
Yeah.
Okay, well, didn't we already calculate this over here?
29.4 radians.
Okay, so 29.4 radians.
And how much time do we just calculate?
Well, it takes 2.8 seconds. 29.4 radians divided by 2.8 seconds, and I get 10.5.
10.5.
10.5 radians per second. And it is just like, it's just like velocity. It's similar to velocity. If I was going a slow radian per second, I would be going,
That's not many radians every second.
if I was going a faster,
That's a lot of radians per second. I'm
Right, so
getting
it's-
dizzy. I'm getting
it's-
dizzy.
it's-
I'm getting dizzy.
it's just like speed, right? Like, it's very similar. Just a fancy new name, okay? So,
Let's do a simpler one.
okay, I'm gonna erase this, yes? A car with a tire of a radius 0.42 meters is moving at 15 meters per second. What is the angular velocity of the tire?
I noticed that we've got a linear speed, 15 meters per second, and we want an angular speed. How do we go from linear to angular?
We use our Rosetta Stone, which we didn't really talk about. Did we forget to talk about that?
We didn't talk about it.
We didn't talk about it.
We expect that the students know what the Rosetta Stone is and what the deuce we're talking about.
Okay, so I've got all of my information down here. I've got my radius, my velocity, and I'm trying to find omega. Okay, so what Boykin is saying is we're given velocity, which is linear speed. And so if we want to know, we're going to have to do a couple of things here. We know that the S equals R and theta, yes?
Yep.
And this is going to be my linear speed right here.
And omega is...
Oh, and
Well, the omega is delta theta over t. So we need to get the theta.
this is what we're trying to find here because we have the radius too, right?
Yep.
So let's go ahead and just plug this in. S over R is going to be, my S is this one right here. The
15
stripe on the
meters.
ground. You know, this is important though. The S, think about it as the stripe on the ground, and that's what our wheel is going to make when it goes 15 meters on the ground in 1 second.
In every second. In 2 seconds, it'll go 30 meters.
Uh-huh.
So if you're like peeling out, if you're like doing a burnout, it's going to leave a stripe 15 meters long in 1 second.
Okay, so 15 divided by 0.42, 35.7
Now I noticed the meters cancel. What are the units going to be?
meters, 35.7. My unit is going to be
The units of angles, which are...
radians.
Boom!
Now, is it, why is that second there still? Ignore it.
Well, we can use that up here in omega. I notice omega is delta theta over delta t, so that's going to be radians per second, I think.
It's kind of like this though, right? Because
Yeah.
like it's really only 15 meters here, right? Is that how I should think about it?
Yeah, okay, but
Eh.
no, I'd leave the seconds
Leave it
on.
there. Okay. All right, so now we've got radians. So during this time, as it's going 15 meters per second, it has a radius of that. It rotates 35.7 radians.
Yeah.
Now, what is the angular velocity here? Let's just put this.
I think it's going to
here.
be the same because what we should have here is we could include in that equation, instead of delta theta, we could have S over R.
Oh yes, yeah.
No, but leave the,
Oh, okay,
leave
yeah,
the
yeah,
delta
okay.
theta, but then equals S over R over delta T. Now, we've already got the answer.
S over R is this radians. But what is the time that we do this in?
That's in 1 second.
1 second, which is really just radians per second.
35.7 radians per second. See how simple that is?
Yeah.
The key is going
Oh,
from...
perfect. You see, because that's there. Anyway, sorry.
Boom, boom.
It's there. I was like, how am I supposed to explain this? Okay. All right, so just to kind of track back to what we did, we have linear velocity, but I'm asking for angular velocity. So we have to use our Rosetta Stone. Our Rosetta Stone takes us from linear to angular in order to find this angle right here. Once we've got the angle, then we just plug it in here. And what's super important is that our velocity right here, this is our stripe on the ground.
Exactly.
You should write that down. This is our stripe on the ground. And our stripe on the ground is our S.
Yep, that's 15 meters.
And that 1 second goes over here. So it's kind of like it goes 15 and then 1, and then the R we fill it later.
Ba-boom, ba-boom.
Okay. What is I keep saying omega, the angular velocity of the second hand on our clock?
That's going slow. Is this period ever going to be over? OMG.
So let's start with what we know. Get rid of this now. So angular velocity is, right?
Yep.
And it wants to know for the second hand. When we go for our angular displacement,
Let's make one revolution.
well, yeah, 1 revolution. I'm like, what is 1 revolution? 1 revolution is going to be 2 pi radians, right?
How much time does it take to do that?
How much time does it take for the second hand to go all the way around?
60 seconds. Takes a minute.
Okay. So 2 pi divided by 60, and I get 0.105 radians per second.
Means in 1 second, it goes 0.105 radians.
Bada boom.
What about the hour hand? What's going to be different about it's going to go slower, yeah?
Uh-huh. So again, same thing.
For the hour hand to go around.
Okay, the hour is going to be 2 pi.
Oh, hold on a second. If the hour hand goes around once, how many hours is that?
1 hour.
That's, well,
Oh, how many?
if the minute hand goes around once, it's an hour. But if the hour hand goes around once, that's 12
Oh,
hours.
12 hours. Yeah.
Oh my God.
So how can we make that into seconds?
Well, let's see. There are 60 seconds times 60 minutes times 12 hours. 60
Times 60 times 12.
times 60 times 12.
I'm gonna get that big old number.
Is it 42 something?
It's 43 something. So
43,000
4,200
seconds.
seconds. And that's gonna get me 2 pi divided by my answer. And I get 1.4, we'll call it 1.5 times 10 to the -4th radians per second.
-4 or -14?
-4. Didn't mean to write the 1. Too excited, not that small. Okay.
So
all
that's
right.
a very slow angular velocity.
Moving real slow. This is a small number. Negative
Yeah.
exponent, small number. Vinyl albums spin at 33.10 RPMs. What is their angular velocity in radians per second?
Here's 33.3 revolutions per second. Ready, mark, get set, go. 1 revolution.
Okay, 1 revolution equals 360 degrees radians. Okay, so we want to go to what is their angular velocity in radians per second. So we just need to get the units here. So we've got revolutions.
Let's put revolutions on the bottom.
Yeah, so 1 revolution is 2 pi radians. Okay, so we got the radians on the top, and let's go ahead and get rid of the minutes. 1 minute is how many seconds?
60.
Seconds. So then I cancel, revolutions, minutes cancel, my units are radians per second.
Top times top times top divided by bottom times bottom times bottom.
Okay, so 33.3 times 2 pi, and I'm gonna divide that by 60, and I get 3.5. 3.5 radians per second.
So you want to know what 3.5 radians per second looks like?
There it is.
radians per second.
Okay. Angular velocity, omega, is a vector quantity. That means
You know what? There's something wrong with this calculation. It can't be
Yes?
3.5 because that means, well, no, because in one, on your mark, get set, go, 1 Mississippi. No, it goes less than 1. Well, 3 radians, because 2 pi radians is 1. Could you check your work on
Yeah.
that? Something smells bad.
so 33.3, and I multiply it by 2 pi, right?
2 pi
And I get that.
divided by 60.
Divided by 60. Yeah, I get 3.5.
Okay, all right.
Well, let me make sure I get
No, that's right.
Okay.
No, you did it
All
right.
right.
The old man's losing it. What old man? This old man.
Okay, so angular velocity is a vector quantity, which just means it has direction. The direction component of the angular velocity is along the axis of rotation, determined by the right hand rule. What the heck?
Funny
is that?
thing about your right hand, or either hand, you can only bend those fingers in one direction. If you try to bend them back in the other direction, they don't work.
Don't do it.
Don't do it.
Okay, so I'm gonna hold it like this. So if the direction of the rotation is this way, I'm gonna curl my hands that way, and that means that the angular velocity is pointing towards me. So
Your
fingers,
fingers are curling in the direction of the rotation,
and my
and the
thumb.
thumb points. So curl them fingers, girl. There you go.
Okay, and then how about if it goes like that, right?
So now it's curling in the other direction.
And the
The
angular
thumb
velocity.
is pointed in the other direction.
Yes,
All right.
yes. Boom, done. It's kind of fun stuff. Yeah, stay.
Stay. Sit.
This is better than my dog. Okay. And now for your homework. So you're gonna read page 197 through 200. You're gonna do number 3 on page 211, and you're gonna do numbers 1 through 3 on page 212.
You can do this.